All righty, friends. Good to see you one final time here on Unit 2B. So I covered a lot of information last class about rational functions. We've covered wholes, zeros, y-intercepts, vertical asymptotes, horizontal asymptotes, slant asymptotes. Today is pretty much a review of that. We're just going to add a little bit more to it. There's nothing really to go too much over. We can pretty much jump right on into it. But what we're going to do is we're just going to kind of literally review everything, kind of pull all the function stuff we've been doing together, which is kind of probably fairly nice. All right, let's see if I can't go ahead and write up what we're going to be doing here today. So we're going to be finding all of these things today. For a bunch of functions. And then we're also going to be sketching these as like normal. So this is essentially everything we're going to be doing here with a given function. So starting off just like last time, we always want to begin by essentially factoring our functions. So let's go through, let's factor our functions, and let's see what it is we're actually dealing with here. So why don't you guys go ahead and do this. And I want you guys to see if you can do the first 6 things: the asymptotes, the whole, the zero, the y-intercepts. Let's see how you do, and then we'll go from there. All right, let's go through and check to see how you did there, huh? All right, so if I were to factor both the top and bottom here, I notice I really like my first term to be a positive x value. So I'm going to factor that -1 out. And when I factor the bottom, I get 2x minus 5, x plus 4. And that's kind of a pretty darn good thing there for us. It means I'm going to have an x value of a whole. So we can simplify this just a little bit. -1 over x plus 4. So that's the function we're dealing with. But remember, we have a whole. X cannot be equal to 2.5 or 5/2, because that was the common factor we were able to get rid of. All right, so here we go. Vertical asymptote. That's where we take our denominator. And we are going to set it equal to 0. So x cannot be equal to -4. That's our vertical asymptote. X can't be equal to -4. All righty, so x equals -4. That's our vertical asymptote. And let's see, if I'm looking at my horizontal asymptote, I'll do that one next. I'm looking at my degrees here. And if you notice the degrees here, I have 1 in my numerator. I have 2 in my denominator. And since 1 is less than 2, that means my numerator is less than my denominator. So that means my horizontal asymptote is y equals 0. And because I have a horizontal asymptote, that means I do not have a slant asymptote. Can't have both, one or the other. So y equals 0. And D and E. Well, friends, we did have a whole. That was when our x value was 5/2. So when x is 5/2, I got to go through and figure out what the y value is. This is where our complex fractions come into play a little bit, because I'm going to have a complex fraction that I have to deal with. Since I have 2 in my denominator, I'm going to multiply every fraction by 2. So times 2 times 2 times 2. Technically, that's not right there. I should have done a little bit better job with my notation there on that. I can fix it now, though. And when I plug in my 5/2 in, I'm going to end up getting -2 over 13. So that'll be the y value of my whole. My zeros, well, friends, I don't have anything in the denominator. There's no x's in the denominator. That means there is no zeros. So let's go ahead and write all this stuff up here now. I got 5/2 and -213. My zeros, I don't have any. My y-intercept, I haven't done that yet. Let's do that real quick. If I plug 0 in, and if you notice, it's literally the same thing we did yesterday, right? So this is good. It's nice. Ends up being a real nice little review. And friends, let's not kid ourselves. I know we probably need a review on it because we are really doing quite a bit here. 0 over 5, 0 plus 0 minus 20. So that means my y-intercept is going to be -1/4. All right. Now, before I do all the rest of it here, I'm going to go ahead and graph it so we can see it. Okay, let's see here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So we're going to go ahead and graph everything. I got a vertical asymptote. When x equals -4, well, that'd be right about here. All right, so there's our vertical asymptote. We have a horizontal asymptote when y equals 0, so literally right along the x-axis there. And remember, the horizontal asymptote exists when my graph is going to positive, negative. Our slant asymptote didn't have one because, well, you can't if you already have a horizontal asymptote. We have a hole at 5/2, that's 2.5, and -213, so that'd be right about here. We had a y-intercept at 0, -1/4, that'd be right about here. And we're going to now go ahead and play connect the dots. So let's see here. And again, it doesn't need to be exact. It can be a little bit of a rough outline. We do need to figure out, though, make sure that the graph is above or below the horizontal asymptote here. So what's that? 1, 2, 3, 4. If you plug -5 in here just real briefly, just to figure out where exactly it'd fall. I'm just going to plug that in real quickly to figure out where that point would be at. I'd get a -1 over -5 plus 4, which is a +1. So when x is -5, the y value would be a +1. So that helps me out a little bit to know where my graph's going to go. So knowing that now, I can make my graph a little bit better. So I usually like to plug in at least 1 point if I am trying to actually do a little bit better sketch. I know last time we just said kitty corner, but sometimes I like to know the steepness of it. So which is why I went ahead and did that. So domain. If we look at our graph here now, domain, remember, that's all the x values. So why don't you guys go ahead and take a second, see if you can come up with domain, range, increasing, and decreasing. All right, friends, let's try. So the domain, realize it's going to be all real numbers, except there's 2 values that x can't be equal to. X couldn't be equal to -4, and x couldn't be equal to negative or positive 5/2. Every other x value works. So by putting what the 2 x values it can't be, I'm telling myself that it can be everything else. Range, if you look at the range, there's 2 y values that it can't be. First of all, it can't be the asymptote. I'm sure everybody got that one. It can't be the asymptote. But what was the y value of the whole? Because that's another y value that it cannot be equal to. So that other y value it can't be equal to is -2/13. That's the y value of the whole. Now, if we look at the graph here, looks like this entire area, the entire area over here, I am increasing. And down here on this branch, I'm increasing the entire way as well. So it looks like I'm actually increasing the entire time. There is no decreasing. In fact, that is the case. So for increasing, I'd say x, just like before, x doesn't equal -4. And x doesn't equal 5/2. And decreasing, well, decreasing, no, there is no decreasing part, so we just say it does not exist. So this is what we're doing today, friends. We're going to just kind of tie the whole thing all up together. All right, now, my friends that have already printed up their notes, great. You already have them in front of you, so you guys can move on to the next problem. For those that don't, let me go ahead and give it to you. So you guys can actually go ahead and try it as well. x² minus x minus 6. And x² minus 4x plus 3. All righty, friends. Why don't you guys go ahead and do me a favor, pause the video right now, and you guys can go ahead and try this with the next equation. So here's our next equation right here. Go ahead and pause the video and see if you can't do all the same stuff we just did for this next function. All right, you guys are putting the finishing touches on it now. Let me just go ahead and erase everything. I know you're probably saying the same thing as before. Just clear the screen. I just don't want to have to write everything all over again. And again, I get to play with Magic Eraser. Watch my kids play that Mario Maker. They can get Mario to jump all over the place, do all kinds of crazy things. Well, I can do that with Magic Eraser here. I'll tell you what. There we go. All right, so just again to start off, you guys would have had to have factored this. So I have x minus 3, x plus 2, all over x minus 3 and x minus 1. And again, if you notice, we have an x value that cancels out. That x value is going to be, x can't be equal to 3. That's what cancels out. All right, here we go. Vertical asymptote. Whatever is in my numerator left over, that would be my vertical I'm sorry, my denominator, that'll be my vertical asymptote. So x minus 1. So x equals 1. Horizontal asymptote. Let's take a look here. Oh, where are we at here? I got 2 and I have 2. Oh, they're the same. Okay. No harm, no foul there. If they're the same, that means I'm going to be looking at the leading coefficients. All right, so since 2 equals 2, that meant the degree in the numerator was equal to the degree in the denominator. So that means my horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. So y equals 1. It's my horizontal asymptote. And again, that exists when I'm going out to negative infinity on the x-axis or positive. Since I have a horizontal asymptote, that means, friends, again, I do not have a slant asymptote. Cannot have both. All right, the whole. I know that x equals 3. That'll be the x value of my whole. And I'm going to plug it into the simplified function to figure out the y value. So we have 3 plus 2. And 3 minus 1. So we end up with 5 halves. So my whole is going to exist at 3, 5 halves. Got to get the zeros now. That'll be the numerator. So I have x plus 2 in the numerator. So x equals negative 2. So I have an x-intercept at negative 2, 0. The y-intercept. That will be when my x value is 0. So let's see, if I plug 0 in there, I get 0 minus 0 minus 6. And I get 0 minus 0 plus 3. So my y-intercept is negative 2. Well, friends, I believe we can go ahead and do the rest of the stuff here, right? So let's make a graph. Here we go. Let's do black. And we'll go 5 across. All righty, friends. So I had a vertical asymptote when x equaled 1. Let's plug that in there. A horizontal asymptote when y equaled 1. And I had a whole at 3, 5 halves. So 1, 2, 3, 1, 2, 5 halves would be right about there. So I had a 0 and x equals negative 2. I don't need to add any points this time because at least I know where everything's going to be located. And I had a y-intercept at 0, -2. So we're going to play connect the dots. So that means the graph's going to come down here through the hole. Ooh, all righty, there's our first part. And then this one. All right, if you haven't had a chance to do it yet, find domain range increasing, decreasing. All right, let's see how you did. So I know it can't be equal to the vertical asymptote, and I know it can't be equal to the x value of the hole. So x can't be equal to 1, x can't be equal to 3. Well, the range can't be equal to the horizontal asymptote, and it can't be equal to the y value of the hole, which was 5/2. Let's see what the graph's doing here now. I'm going left to right, I'm going down the entire time, that's decreasing. Left to right, I'm going down the entire time, that's decreasing. Well, in this case, the opposite of the last time, I don't have anything increasing. Instead, I am decreasing the entire time. So again, that means the decreasing domain is equal to the domain itself. All righty, friends, let's try one more, and then we're going to call it a day here. One more, then we'll call it a day. That'll finish off Unit 2B. Or not 2B, 'tis nobler. All right, no Shakespeare. F of x equals 2x squared plus 5x plus 11. All over x plus 1. So in your notes, if you scrolled on down, if you print them up, number 3 would be this function. For those of you that didn't print them up, there you go. I want you guys to go ahead and pause the video and see what you can do with that one. Go for it. All right, friends, let's try it here. So we got to first figure out what if there's any holes. Well, tough break, or maybe good break, I don't know. The numerator doesn't factor, right? Numerator doesn't factor. So in that case, I don't have to worry about any holes then. So we do have a vertical asymptote. So x plus 1 equals 0. So that means I have a vertical asymptote when x equals -1. So, and again, just for the reminder of it all, the top part does not factor. So let me draw a little arrow to that so remember that. The numerator does not factor. Okay. All right, let's go to talk about our asymptotes a little bit. I have a 2 here. I don't have an asymptote here, so I got to put one in there real quick, or x1 here. Here. And I have a 1 here. So that means, friends, my horizontal asymptote, 2 is greater than 1. That means my numerator is greater than my denominator. And when that happens, that means I do not have a horizontal asymptote. And if I don't have a horizontal asymptote right now, bells and whistles should have gone off in your head when you did it. It means we had a slant asymptote. So let's go find that slant asymptote. So x plus 1 equals 0. When I divide by it, that means I'm dividing by -1. So -1 went in my box. The coefficients, 2, 5, and 11, went outside the box. Now I got to divide everything inside the box. Here we go. Add going down, multiply by the box going up. 3, -3, 8. And like we said before, because there's a remainder, that means it didn't go in evenly, which means there is a slant asymptote. Okay? So again, since I start with x squared here, then I'm going to drop it by 1, so I have x to the first plus, so y equals 2x plus 3. That is my slant asymptote. Well, since the top didn't factor, there is no hole. There was none. We didn't have, there's no factors in the numerator that also were in the denominator. And again, we saw that, first of all, with the slant asymptote, didn't divide evenly. Second of all, I wasn't able to factor my numerator. How about the zeros? Since it doesn't factor, that means in order to figure out the zeros, I'm going to have to use the quadratic formula. I'll set my numerator equal to 0 to use my quadratic formula. So x equals a negative b plus or minus the square root of b squared minus 4ac over 2a. It's a great song. All right, so b squared, that'd be 25. Minus 4 times 8 times c, that's minus 88. I can already see something happening here, friends. X equals -5 plus or minus I square root of 63. It's a -63 in the denominator, all over 4. Well, friends, we don't have complex roots here, so that means there are no zeros, no real zeros for me to deal with. No real zeros. There are no real zeros. Won't have to worry about that when I go ahead and graph this. And my last part is my y-intercept. So that's when I plug 0 in. So if I plug 0 in, friends, there we go. 0 plus 0 plus 11. All over 0 plus 1. Turns out my y-intercept is 11. All righty. Well, that means that this graph here is going to be huge. Let's make a big graph. Make a big graph so we can see the dumb thing. And if you guys don't mind, let me put some lines up here. 1, 2, 3, 4, 5. 5, 6, 7, 8, 9, 10, 11. I know my y-intercept's at 11, so I got to get up there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think 10 is probably enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let's compare your guys' graph to mine then. Curious to see how y'all did. Let's go. X equals -1. All right. So I have a vertical asymptote at x equals -1. Then I have a horizontal asymptote at y equals 2x plus 3. So my y-intercept's 3, up 2 over 1. Up 2 over 1. So it looks like I'm coming this way then. Holy wow. All right, so up 2 over 1, that'd be right about here. Up 2 over 1. I'm sure your line will be a little bit more accurate than mine. You'll be on graph paper. No real zeros. Well, okay. I have a y-intercept at 0, 11. So I know I have that y-intercept way up here. Wow. What the stink does that look like? I'll tell you what, why don't you guys go ahead and plug it into your graphing calculator, and do me a favor. When you plug it in your graphing calculator, here's what I want you guys to figure out. Where is the relative minimum at? And where is the relative maximum at? We dealt with graphing calculators last chapter. So why don't you guys tell me, where's the relative minimum at? Where's the relative maximum at? Go for it. Go ahead and hit pause that way, and then unpause it when you're ready. All right, friends, I'll tell you what. The relative minimum, that's the bottom of a hill. Well, turns out the funny part is the bottom of our valley. Well, it turns out the valley actually is way up here at 1,9. And the graph looks something like this up here. Notice the relative minimum can be more than the relative maximum, right? So I have a relative minimum there. All right, that's the point, 1,9. The relative maximum is the top of a hill. Well, the top of the hill, our hill's down below the x-axis. Turned out our relative maximum is -3, -7. Remember, relative minimum is bottom of the valley. That's when the graph goes from decreasing to increasing. Relative maximum is the top of a hill. It's where the graph goes from increasing to decreasing. 1, 2, 3, 4, 5, 6, 7, right over here. Looks like it's going to be kind of down here in this area. And the graph comes down here like that. We'll write that coordinate there just so we have that as well. -3, -7. So again, you can kind of see how we have the hill down here. And again, we know it's a relative max because the graph goes from increasing to decreasing. And we know that this is a relative minimum. You can see the valley up here at the top because it goes from decreasing to increasing at that relative minimum. So relative minimum max, realize again, those aren't the minimum max points of the entire function. That's just what it would be for that particular case. Just in that local area. If I were to zoom in on it, that's the lowest or highest point in that local area. Our domain, well, it was every value was okay except for x couldn't be equal to -1. But our range, realize our range went from -infinity, and then it went up to this value right here. So it went up from -infinity up to -7. That's the y value of the relative maximum. And then I had the y value of the relative minimum, which would have been at, notice those are brackets, 9, and I'm going out to infinity. And again, these are parentheses around the infinities. All right, increasing and decreasing domain. Remember, increasing and decreasing, those are x values, not y values. So I'm going from -infinity, since it's increasing here, -infinity up to -3. That's a parenthesis there. And then I went from -3 to the asymptote, -1. And I go up to the top. I was decreasing here from -1, the vertical asymptote, to the relative minimum, to 1. So -1 to 1. And then I increase from 1 up to infinity. So hopefully you guys got some that match that a little bit. So, well, friends, we'll be playing more of these graphs and domain, range, increasing, decreasing, asymptote, poles, zeros, intercepts. We'll play with more of it tomorrow in class as we put a kind of tie a bow around this little chapter and wrap it up. So I'll see you guys in the morning.